Okay, guys, this is the last lecture in the waves unit, and this one's going to cover the electromagnetic spectrum and characteristics of electromagnetic waves. Pretty cool. So we can see visible light, okay? And visible light kind of covers all the colors we can see, all the different colored lights, which allow us to see, the various colors in our experience here. But there's a lot of light you can't see, so we call these all the waves that we can and can't see EM waves, or electromagnetic waves. So if you think back to the previous chapter, these waves, remember, are made up of electric fields and magnetic fields, sort of alternating, right? They kind of go perpendicular to one another. So there's different kinds of waves, lots of different kinds. So X-rays, radio waves, microwaves, those are all EM waves. So all of these EM waves travel at a speed of 300,000 kilometers per second. And what is that speed? Should ring a bell. That's the speed of light, okay? And it travels that speed in a vacuum. So remember, when waves are exposed to different mediums, right, like water or air, light can slow down, and it does slow down just a bit. But in a vacuum, all of these different kinds of light, X-rays, radio waves, microwaves, they all travel at the speed of light. So as I said before, we only see part of this whole spectrum, right? And a spectrum, I should say, is really just another word for a system of organization, right? And it's usually a system of kind of opposite kinds of something, right? When you have a spectrum, right? Like a spectrum of colors is a commonly used thing, right? It's sort of polar opposites, right? On one end you've got warm colors, and one end you've got cold colors. So there's like a spectrum in between. So a spectrum just meaning like a system of organization. So within this existing spectrum, right, this whole thing here, we can see only this portion in here, right? So we only experience directly, right, with our sight, these colors, these red, orange, yellow, green, blue, and violet light, right? So it's just a small sliver of the actual whole electromagnetic spectrum, right? So all these ones that we're going to kind of be talking about here in this lecture are types of light that are not visible. Now, they're there all the time. They're around. They're contained within light from the sun, but we don't directly experience them with our sight unless we have special contraptions, which we'll talk about in this lecture. So again, all the waves that were just on that slide are part of the electromagnetic spectrum, right? We kind of divide that system of organization up into different regions according to the length of the waves. All right, so some types of light waves have a larger wavelength than others. Remember, the wavelength is just the distance between crests on a wave. All right, so you can see here the difference in the size of the waves. Okay, so radio waves sort of begin things here, right? They have a lot larger wavelength than gamma rays, which are on the other end of the spectrum. Remember, so the spectrum is the entire system, right, of organization here. So wavelength is what we use to organize the system. You should know that, right? So I'd write that down somewhere. Wavelength is used to organize EM spectrum. Abbreviate that, okay? So wavelength is used to organize the electromagnetic spectrum, right? So we always have something to organize systems, right? If you go to the grocery store, right, we group foods by types of food or by the temperature they need to be stored at, right? If we talk about anything in an organizational system, a library, right? Books are organized by like type or by a Dewey Decimal System number, right? There, we just use wavelength to organize light, okay? And it falls somewhere on the spectrum. So the first type of wave on the electromagnetic spectrum we're going to talk about are radio waves. So radio waves actually, if you look at that previous picture on the last slide, make up pretty much the longest part of the EM spectrum. They have some of the longest wavelengths and the lowest frequencies of all EM waves. So when we think about that, we think about them having long wavelengths, right? So there's a long distance between the crests of each of these waves, okay? And they have low frequencies, meaning there's less waves, right? There's less crests in the stretch of radio waves, all right? So that's significant, right? They're used for broadcasting radio signals, and they make great radio signals because they're so long. They can travel really long distances. Not very fast, right, because they have a low frequency, but they can go really long distances. All right, so if we think about anything longer than 30 centimeters wide, right, so 30 centimeters plus is considered a radio wave. So there are two sort of things that we do to encode information in these radio waves. We can either vary and change the amplitude, so like the height of the wave, right, or its frequency. Okay, so if we change either the amplitude or frequency, we can encode information, right? This is called modulation. So AM, as an AM radio, stands for amplitude modulation, right? So that's changing the height, right, of the wave. And FM modulation stands for frequency modulation. So that is changing, right, how, the number of waves that frequent that stretch of wave, right? So if you think about AM versus FM then, so FM would have larger or smaller wave amplitude, right? So this would be AM. And FM would be more concerned about encoding information, in this case sound information, right, like music or talk radio, into the number of frequencies, the frequency of the waves. All right, so each type of radio waves changes or modulates the wave in this type of way. All right, so you should know AM and FM. So I've already alluded to it in class a bit, and you could see it in that last slide a bit. So AM radio waves have longer wavelengths than FM radio waves. They can actually bounce and off the atmosphere, right, as opposed to continuing to travel out into space. They can be picked up from really long distances, right? So you can hear AM stations from places really far away because of that. So I'd also point out too that radio signals aren't on the radio aren't the only thing that radio waves carry. They also carry TV signals. So these are broadcasts on shorter wavelengths and have higher frequencies than radio stations, right? So meaning they have really short wavelengths, right, and really high frequency. That's a terrible drawing, but have really high frequencies. So that just means that they carry more information, right? So because they use such short wavelengths, you can encode a lot of information, right? So these signals are really high energy signals. So a TV radio wave versus a radio wave is going to have a lot more info and a lot more energy and travel a lot faster. All right. Microwaves are the next type of EM spectrum we're going to talk about right now. So they have shorter wavelengths and higher frequencies than radio waves. So they're between 1 and 30 centimeters. Because remember, 30 centimeters and up is how large the wavelength is for a radio wave. So we're getting shorter as we go, down the spectrum, right? And so we're having these waves have more energy and can do different things. So microwaves have a magnet inside that accelerate particles. So that reflected fan kind of moves those accelerated particles around, kind of creating a little bit of a convection current inside this inside the oven here, right? And then your microwaves actually then penetrate your food, and they excite the water molecules in your food. So if you ever wonder how a microwave works, well, those waves work better when you've got food that has some moisture on it, right? So it excites those particles, right, and increases their energy, right? So Um, that's why if you're cooking something that's really dry, like let's say if you put some like dry rice in the microwave, it's not gonna heat up very well. If you add a little bit of water, it's gonna heat up faster, right? So um, actual microwaves actually penetrate your food and go into your food. All right, so microwaves are also used in communication because they, have a little bit more energy, have shorter wavelengths. They can carry more information than a radio wave can. So cell phones use microwaves. So when you're texting, when you're calling people, you're actually sending a microwave to a satellite in orbit, right? So pretty cool. So microwaves are also used in radar. And if I didn't know this, prior to a few years ago of teaching, that radar is actually an acronym. So it stands for radio detection and ranging. So when you ping, right, when you send a microwave out from a radar station out towards something, it bounces off whatever you're sending it at, right? Whether that's a car, or whether that's a fighter jet, right, in an enemy airspace. That microwave reflects off an object and returns back to the transmitter. So that wave is used to calculate speed. So when your parents get a speeding ticket, that's thanks to our harnessing of microwaves, right? That little radar gun fires out a microwave and bounces off their car and gets them a ticket based on how fast they are, right? So pretty cool. The next type of wave is an infrared wave. So we're moving down the spectrum, right? So these have even shorter wavelengths between 700 nanometers up to 1 millimeter, right? So you can still kind of conceptualize how big an infrared wave is, because a millimeter is like a really small amount between your two fingers. You can kind of visualize that. Almost everything gives off infrared waves, including the sun, buildings, trees, and your body. The amount of infrared waves an object emits depends on the object's temperature. Warmer objects give off more infrared waves than cooler objects. So an infrared camera, right, picks up these heat waves, right? So you can also think about infrared waves as heat waves. So infrared is heat, okay? So we know from the previous chapters, right, that more objects that are warmer have a higher kinetic energy. The particles are moving at a higher kinetic energy, right? So they radiate more heat. And therefore they radiate more infrared waves. And have you ever seen those kind of infrared cameras, where someone's heat signature is shown up, right? You can kind of see it as a brighter color, like an orange or a white, versus the cooler blues and reds. That's how they work. They detect these infrared waves that come from a warm object. So another thing that uses infrared waves is your actual remote control. So your that little light on the end, that little kind of diode on the end of your remote control is sending an infrared wave to your TV. So a really, really low one low in energy, but still an infrared wave. Okay, so the next form of EM energy we're going to talk about is visible light. Right, so we're moving from the infrared waves to the right of the spectrum. We're going to the shorter wavelengths, and so this type of light is the type of EM energy that we can see, that our eyes respond to. Visible light waves have wavelengths between 400 nanometers and 700 nanometers. So the wavelength is decreasing, right? So if we're talking about it like this, it's getting shorter and shorter and shorter and shorter and shorter and shorter and shorter as we go. Okay, so the light we get from the sun is white light. So white light is all the visible light of the wavelengths combined. So when we see something with color, we're seeing some of that color absorbed by the object, right? Like a red cup. If I look at it and see a red cup, all the colors are being absorbed except for that red, which is reflecting and coming back to my eyes. So all colors of light combined are white light. Here we can see the entire spectrum here. So humans can see different wavelengths of visible light as different colors. So each of these individual colors is just a piece of this whole visible spectrum. So the longest wavelengths are seen as red light, and the shortest wavelengths are seen as violet light. So Roy G. Biv, you can see here, is the kind of famous thing here. So When we're seeing just one color, we're seeing just one part of the spectrum. All the other parts of light are there; they're just absorbed by that object, right? So if I'm seeing a blue sweater, all the colors of light except for blue are absorbed. Blue is reflected back to my eye. All right, it's definitely a little tricky to grasp and get your head around. It's kind of a crazy concept, but pretty cool too, I think. So that whole range of colors is called the visible spectrum. Remember, guys, what a spectrum is. A spectrum is a system of organization, right? So kind of putting things often a line to show differences among common substances or concepts. Okay, so now we're moving down into UV light or ultraviolet light. It's another type of EM energy coming from the sun. So these have even shorter wavelengths and higher frequencies than visible light. So from 60 nanometers to 400 nanometers, getting smaller and smaller. So again, that got to get that concept in your head. We're talking about even smaller and smaller wavelength as we go. That was not a very good drawing, but I think you get the picture. So UV light is both bad and good. We have UV light coming right from the sun, so it can cause sunburn, as many of you pale people know, like me. UV light can also cause skin cancer, wrinkles, damage the eyes. Right? It affects the pigments in our skin, causing them to change color or turn red as a sunburn. Right? We know that ultraviolet light is also good, though. So if you've ever seen those UV lights that kill bacteria, right? You can see them lots of times in like doctors' offices and things, or they make lots of sanitizing devices now that you can kind of if you've seen the hand dryers that have that blue light that shine like along with the blowing air. That blue light is a UV light that's killing bacteria on your skin. So it's just calibrated enough so it's not dangerous for your skin, but it will kill the bacteria. So that's a good thing about UV light. UV light also, the right amount, can cause your skin cells to produce vitamin D, which is really great for a lot of things: overall health, fighting cancer, for mood, for a lot of different things. So UV light is both good and bad. All right, so X-rays, most commonly thought of when you think about like a superhero, right? You think of like Superman's X-ray vision. So that's obviously fictional, not real, but X-rays have even smaller wavelengths. So we're getting toward the end here. They've got wavelengths between 1,000th of a nanometer and 60 nanometers. So on the smallest end, they're really tiny at 1,000th of a nanometer. At the large end, 60 nanometers. They can pass through material, so they're so small, they're so kind of highly energetic, and have such a high frequency they can go right through most solid objects. So obviously we use those to take X-rays, right? So how the X-ray machine works is that X-ray will pass through your skin, through your muscle tissue, through your fat, and it will kind of bounce back when it hits something a little more dense, like the bone. And that's why you can hold your hand up to an X-ray machine. You can see the bones inside, right? So we use that to find out, if you've got a broken arm or something. However, X-rays, because they have so much energy, because they're so such that high frequency, they can kill your cells. They can kill living cells, and that's why if you've ever gotten your X-rays at the dentist, you wear that lead vest. Right, that vest protects you from the X-rays in parts of your body where you don't want them. Right, so we put the X-rays a small amount on your jaw or your part of your body you're wanting to examine, but we want to exclude the rest of your body because exposure to too many X-rays can cause cancer, can cause death of cells. Okay, so here's a picture sort of describing what I just talked to you guys about. How the X-rays can pass, right through the skin there, and they strike a film, right, which you can either take a picture or show like a live video sometimes too. And you can see the picture on the right of the broken bone. That's a really broken bone. That's not good. Ouch. Okay, and the last type of electromagnetic energy on the EM spectrum is our gamma rays. So gamma rays have the shortest wavelength, all right? So we're talking like, just like that, like super tight, like that at the end, and they can penetrate most materials easily, right? So if X-rays could penetrate our skin and our muscles, gamma rays can pretty much go through everything, including bones and most forms of solid matter. Gamma rays are used to treat some forms of cancer, however, okay? So they do have uses, right? So they focus a gamma ray, like a really small amount of these gamma rays, on tumors in the body to kill the cancer cells. So we've kind of taken this really dangerous thing, and we've harnessed it in a positive way. So, and when I say narrow, we're talking, a tenth of a nanometer in size. So a tiny ray of these gamma rays is used to pinpoint and target almost individual cells, right? So that's how good we're getting with gamma rays and how precise we are. So they also are used to kill bacteria and foods, kind of like the way infrared UV rays are as well. So there are some uses. So to going from harmless, right, all on one end, right, radio waves. I mean, radio waves are flying through my body right now, right? You can't really avoid them. Radio waves are being broadcast from left and right, and they don't harm you. They're low in energy. They can go right through you or right through lots of matter and really not do any damage. All the way down to the other end of the spectrum, where we're talking about gamma rays, and gamma rays, because their wavelength is so short and their frequency is so high, they have a ton of energy in them, right? And waves are just transfers of energy. So these gamma rays are dangerous. All right. So when you're getting ready for the quiz, guys, make sure you can tell the difference between all these different forms of EM energy. There's going to be a little matching section where you'll have to just know the definitions cold and know how the whole system's organized, right? It's organized clearly by the size of the wavelength, right? The length of the wavelength is the key thing that we use to organize this system, all right? And, visible light is probably one of the more harder concepts to understand, this idea of white light coming from the sun being broken up into different colors. When you see a rainbow, how that works is it's water molecules breaking up that white light into all the individual colors. All the colors are always there, but it's just what's reflected back to our eyes is what makes the colors perception to us. Okay, so study, and I know this is a long lecture, but I love this kind of stuff, and I'm looking forward to doing some cool stuff. We're gonna make some spectrometers and actually see these forms of light as much as we can safely. Okay, and study, and I will see you when I see you. Thanks.